Hello, this is Taylor Hernandez reporting live here to talk about rectangular waveguides. This is for the final project in E&M. In vacuum, we have that the divergence of the electric field is zero. The curl is equal to the rate of change of the magnetic field, which is Faraday's law. We have that the divergence of B is zero, the no-mag's law. And then we have that the curl of B, which is just Maxwell's law. The important thing that we realize here is that electromagnetic waves are transverse. Now we're going to look at what happens when we confine these waves, rather waveguides. E and B are both zero inside, and we basically just subject these to boundary conditions and solve for the components of E and B fields. When the Z component is zero, the electric field, we have TE modes, and similarly we have TM modes for when the Z component of the magnetic field is zero. For a rectangular waveguide, that we consider a rectangular shape, and we're only interested in the propagation of the transverse electric waves. To solve this, we do it by separation of variables, letting the Z component of the magnetic field equal functions of x and y. The general solution is a sum of sines and cosines, but the boundary conditions require that the x component of the magnetic field is zero. So we have that there's only cosine components, and our wave numbers are confined in a similar way. These solutions are called the transverse electric MN modes. The first index is conventionally associated with a larger dimension. So for the purposes of my project, we always have that A is greater than B. One of these indices must be non-zero. If you have a frequency that's less than your lowest cutoff frequency, then waves won't propagate. When you have imaginary wave numbers, then the traveling waves we have will become attenuated fields. Rectangular waveguides are commonly used to connect feeds of signals to their electronics. For example, low noise receivers or power transmitters. Another example is with impedance matching. This is an important feature for matching the specific components of a circuit. If you consider, for instance, a waveguide connected to antenna, and you wanted to know how much of the wave will be transmitted or reflected, you will have to calculate the impedance ratio. But by connecting a waveguide to an antenna, you can simply just match the impedances and control the propagation. This is again because the propagation mode in a waveguide is one solution of the wave equations, that is, a specific form of the wave that is dependent on the boundary conditions.